Hello, my name is Noah Brüstle. Today I am going to be presenting approximation algorithms for hitting subgraphs. This is joint work with my professor Hamed Hatami as well as Tal Elvas, Onur Kashur, and Bing-Chan Ma. First, we will define our problem. For two given graphs H and G, a subset S of the vertices of G is considered to be H-hitting if G without S does not contain a copy of H. The H-hitting problem then consists of finding a minimum set that fulfills this condition. For example, here, our graph H has several copies inside of our graph G. And our objective is to remove all of them. We can then, for example, remove these two vertices, in which case there will be no more copies of H inside G. Further, we know that this is minimal because each of the red copies of H and G need at least one vertex removed, and they are disjoint. In a certain sense, the H-hitting problem can be seen as an extension of the vertex cover problem, which is simply the H-hitting problem for an H that is equal to a single edge. Alternatively, the H-hitting problem is a subset of the hitting set problem. Given these two, it may not be surprising to find that the H-hitting problem is NP-complete for every connected graph H that has at least two vertices. This is something that we have proven inside of our paper. Given this NP-completeness, it is fairly obvious that what we will be studying then is the approximation algorithms. For any graph H, we have access to a trivial approximation of a value of k, where k is equal to the size of our graph H. This is done as follows. While the set of copies of H in G is non-empty, we choose a random copy of H, remove all of its vertices, and then check again if there's any copies of H left. So for example, taking what we used before for our G, we could start by removing every vertex, not only one, but we really remove every vertex from our first copy of H. Then we remove every vertex of our second copy of H. Then we can check that there's no more copies of H left. This will necessarily be a K approximation because each of our copies of that we removed need at least one vertex, need to have at least one vertex removed from them. And since they're disjoint, we cannot do that simultaneously. For certain H, however, we can find better approximations. For example, one problem that has been studied a lot is the H approximation problem for the three paths. A recent result in 2018 showed that we have access to a 9/4 approximation instead of the trivial 3 approximation. More generally, for kth paths and k stars, a result by Guruswamy and Lee in 2017 showed that we have a log of k approximation, of course, not log of n. That's a small typo here. The question we then ask, which graphs allow a non-trivial constant factor approximation? For the purposes of this paper, we will call such graphs that allow a non-trivial approximation to be approximate easy. In 2017, Guruswamy and Lee were able to find a very interesting result in this regard, assuming the unique game signature and that NP is not subset of BPP. No two vertex connected graph is approximate easy. Motivated by this, we propose a conjecture that every graph that is not two vertex connected is approximate easy. However, we were not able to prove this fully, though we made some progress in that regard. The three results that we look at in our paper are the following. Firstly, we extend the results by Goswami and Lee to the case of induced graphs as well. Secondly, of course, as stated previously, we show that indeed for every connected edge with at least two vertices, the edge hitting problem is NP-complete. And then finally, we will show that all trees and several other graphs are approximate easy. In this short section, we will briefly be looking through the hardness result by Goswami and Lee. As previously stated, the theorem states that assuming the unique gains conjecture and NP known as subset of BPP, no two-vertex connected graph is approximate easy. This follows from a reduction from the inapproximability of the K-uniform hypergraph vertex cover problem. We do this as follows. For a certain construction, we find that the following two cannot be distinguished. A, there is an H-hitting set with a 1 over K plus epsilon fraction of the vertices, and B, every set with 2 epsilon fraction of the vertices contains at least one copy of H. We call the first part completeness, second part soundness. The construction looks like this. Given some hypergraph K, which we want to do hypergraph vertex cover, we create a graph with vertices vk times some later to be determined constant b. And for every edge inside K, we add another lambda later to be determined constant number of copies of our graph H onto G. This is a bit technical when you look at it in words, but much easier to explain with an image. So that's what we will do now. Given some hypergraph K over here, we will create a second graph over here, where for each vertex, we create a little cloud of vertices in G. And then for any edge in the hypergraph, we will be choosing at random from the corresponding clouds one vertex each, and on these chosen vertices, we will construct a copy of H. One might then be inclined to ask, why does this work for two connected graphs and not for other graphs? This has to do with the number of unintended copies that are created during the process. An unintended copy is any copy of H that appears not as the result of directly taking some edge and planting a copy on our graph G. It is instead a mishmash of different copies that we have planted. These are much less likely to appear when we have a two-connected graph, because each component that we have that is part of our unintended copy needs to be connected and thus coincide with at least two other components. This makes it much more unlikely for this to happen. So, for example, our green line has to be here and has to be here. On the other hand, if we remove this and just say that our H is a 3-path, then any of the 3 yellow lines would create a valid 3-path. So we will have a lot more unintended copies. This would mess with our proof of the completeness of the problem. In our paper, we further extend this result by Goswami and Lee to the induced case, which is achievable by simply slightly modifying some constants in the soundness case. We will now be showing our NP-Hardness result. More specifically, we will show, as previously stated, that the H-hitting problem is NP-complete for every connected graph where H has at least 2 vertices. This will be done by reduction to either vertex cover or the hitting set problem for 2 connected graphs, depending on the choice of H. We will remember that the hitting subgraph problem for 2 connected graphs is inapproximable and thus necessarily NP-complete itself. In the first case, our graph is a tree. In this case, we will be reducing to vertex cover. This is done by first choosing some leaf in H, removing it, and then remembering which vertex in H was neighboring to it previously to its removal. Then, for some given graph G, we will glue all of our copies of H onto the vertices of G, every single vertex of G, like this, by the vertex that was neighboring. In this construction, we can then see that necessarily any vertex cover on G will also remove any copies of H in the larger structure, and any solution for the H hitting problem on the larger structure will also be a solution for the vertex cover problem on G after some tweaking. Specifically, with tweaking, I mean that if we in our H covering problem chose some vertex which is not inside G, we can simply transport it onto G, because necessarily if some copy of H is hit by this vertex, it will also be hit by this one. The case where H is a graph that has 2 connected components is not very different. We will reduce to the K hitting problem where K is 2 connected. Our choice of K here is some largest 2 connected component inside of H. We note that this component does not have to be unique, simply one of the largest. We then choose we identify the vertices that were connected to our largest component K, and then by those vertices, connect all the hanging loose bits onto our graph G. With this construction, we will be able to notice that removing all copies of K on our graph G will necessarily remove any copies of H inside the larger graph. On the other hand, if we have some H hitting set inside of our largest graph, we will easily be able to transform this into a K hitting set on G by simply, again, transporting any vertices from outside of G onto the connecting edges, connecting vertices, sorry. In the last section of our presentation, we will be looking at approximation algorithms for the H hitting problem for certain H. Our first tool will be something that we call grid graphs. These are subgraphs that we can find in G that we can safely remove without having to worry about no longer having a better than trivial approximation. More specifically, we will define a graph K to be called T-good for the H hitting problem if it is possible to assign non-negative weights to the vertices of K, such that every H hitting set in K has a weight of at least 1/T of the total weight. A bit wordy of a definition, but the important thing to remember here is that we want our T to be smaller than K. It's a bit easier to illustrate. Here, for example, we have a graph H and a graph K. by assigning to our graph k weights of 1/2 to the lower 3 vertices, we are able to ensure that you'd have to remove at least a weight of 1 from the graph k to make sure that there is no more copies of h inside of it, since removing only one of the 3 1/2s still leaves us with a copy of h. Given that k only has a total weight of 5.5, this means that k will be 5.5 good for the graph h. This is important as the graph h itself has a total weight of 6. Now we are able to safely remove all copies of h inside of our initial graph G and still maintain a 5.5 approximation. We will now note that our remaining graph G is certainly simpler, but has fractional vertices because we're removing fractional copies of k, or fractionally weighted copies of k. Thankfully, we have some powerful tools in linear programming that allow us to reduce problems from fractional. For example, a result by Aharoni, Holtzman, and Krivellevich allowed us to come up with the following theorem: that h be a graph on k vertices and t greater than k be an integer. Then we have an efficient k and k times 1 minus 1 over t factor approximation algorithm that solves the h hitting problem for a weighted graph G if we can provide a t coloring of the vertices of G such that no copy of h in G is monochromatic. Basically, what this is saying for us, or at least what is relevant, is that as long as we are able to create a coloring of a fixed size for our graph, for our graphs G, such that every copy of h inside our graph necessarily has more than one color, then we have an approximation algorithm. We will now be giving a definition for something that we have decided to call semi-symmetric cut vertices. Specifically, this is the defining property that the graphs must contain such that our algorithm is able to apply. Definition: for a graph H consisting of m connected graphs f1 to fr, all sharing a single vertex v and otherwise having distinct vertices, we call V a semi-symmetric cut vertex of H if there exists distinct ij element of R, such that Fi is a subgraph of Fj as a V-rooted graph. Again, a bit wordy of a definition, so we will try to illustrate that. Over here, we can see, for example, that the following triangle we will be calling to be rooted at the vertex V, because that's the cut vertex, is a subgraph of this, while equally being rooted at the same V. So V is a semi-symmetric cut vertex. Or let's say another example, if we would have this square and then something like that, then like that, let's say, then this square is a subgraph of this structure while both being rooted at the same vertex V. So this is again a semi-symmetric cut vertex. We will now be providing an approximation algorithm for any graph that has such a vertex. To put that a bit more formally, we have the following theorem. Every graph H containing a semi-symmetric cut vertex is necessarily approximate easy. More precisely, we have an efficient k-1/2 approximation algorithm for the H-hitting problem. We define the following k-1/2 good graphs for H. Given some graph H with a semi-symmetric cut vertex like this, we will choose the larger side of the semi-symmetric cut and attach a copy of it below, attached to the vertex V. Then we will give a weight of 1/2 to all the vertices except the vertex V, which is given a weight of 1 as usual. We can see that this will necessarily have a weight which is smaller than the initial graph H, because if we were to add another copy of the smaller side of the semi-symmetric cut, then we would have a cut which is exactly equivalent. We would have a weight which is exactly equivalent to H. So in this case, it's a k-1 good graph. We add to that another definition. We will be calling central any vertex in G that is isomorphic to the chosen semi-symmetric cut vertex in H for some copy of H in G. We say that a copy of H in G is centered at V if V is isomorphic to the chosen semi-symmetric cut vertex in H. This can be seen as follows, given again our same H. In G, we have here in blue a copy of H, right? In blue here, we have our copy of H. This vertex over here will be considered central in G because it is the semi-symmetric cut of some copy of H. In this particular case, this would also be a central vertex. The copy H prime is said to be centered in V as well. After removing all the previous good graphs, the good graphs being those defined over here, we can construct a directed graph. We start with a new empty graph G prime with the same vertices of G, but no edges. And then for every central vertex V in G, choose some copy H prime of H centered at V and add a directed edge in G prime from V to all the vertices of the copy H prime. For example, in this case, we start with the graph G here. Then we remove all the vertices. Then, given that for our same H as defined over here, this is a central vertex, we will be adding directed edges from V to all the vertices of our copy of H that is centered at V. We have the following lemma. We will be noting that in the previous slide here, this is only done once for every central vertex V. We will then use the following lemma. Every directed graph of maximum out degree M admits a proper 2M plus 1 coloring. This is in essence the same argument as would be used for the more famous maximum degree argument of coloring for non-directed graphs. The proof is as follows. Since the sum of the in degrees is equal to the sum of the out degrees, such a graph must contain at least one vertex with total degree at most 2M. We can remove this vertex safely, color the rest of the graph inductively, and then color this vertex with one of the available colors. We are thus then able to color the directed graph G' with at most 2m colors. This is further sufficient to make sure that no copy of H in G will be monochromatic. Why? This is because for our graph H, since we band any of these structures, then if we have a central vertex, necessarily any copy of H which is centered at this vertex V needs to have some vertice contained inside the adjacency of the directed graph to be able to have a copy of this portion of H. This is then the necessary condition to apply our previous coloring theorem. So then we could, if we were to recall our coloring theorem, we can see that since we have a 2 times k coloring, our result follows immediately. From this result, we will then be able to make our conclusion in trees, because trees are indeed very trivially graphs with a semi-symmetric cut vertice. Indeed, we can just choose any vertex that is neighboring to a leaf, and this will be a semi-symmetric cut vertex. We are now left with the following. First, the hitting subgraph problem is NP-hard for all H. Secondly, no two-connected graph allows an approximation algorithm that is better than the k factor that we get from a trivial algorithm. However, we still have some gaps to fill, while our presented algorithm does, in a certain sense, offer an approximation algorithm for the vast majority of graphs that are not two connected. We, for example, do not have an answer for the following graph. And finally, we have the question of the induced hitting subgraph problem, which we can remark is distinct. Something we can see is that for the induced hitting subgraph, the complement of a certain graph will have the same problem, will have the same difficulty as the problem itself in the induced case, since we can simply flip all the vertices and non-vertices in our graph G. Given that this would show, for example, that several trees are also inapproximable for the induced hitting subgraph problem, since several trees are the complement of a two-connected graph. There are still very few results on what can be approximated in the hitting subgraph, in the induced hitting subgraph case. The only known result, in fact, is a approximation that is allowed for the following 3 paths. We believe that the techniques that we have used inside of our proof for the semi-symmetric cut vertices might also, at least in some cases, apply to the induced case. This might be a nice avenue to explore. Thank you for listening.